Morning, guys, again, and today is March the 15th. Today we're starting a brand new topic, basically, for this class, namely temperature and thermodynamics in general. So let me get my notes first of all, and then we will need this, share. Again, today, like I said, is we're starting kind of a new topic. So I'm hoping that this new topic you guys will follow it through, because as a new idea that comes in, you have an advantage in a sense that you're going to follow it from the beginning to the end, as long as you do all of the examples, as long as you do all of the stuff related to it. Okay, so the idea is, first of all, we're doing chapter 17, as the title suggests in here. And for chapter 17, basically, we're talking about temperature, mainly, okay? We're going to also talk about heat, and there is a big difference between the two in the fact that this one is actually a measure of how fast basically the particles in the system are moving, or I should say oscillating, because they could be moving in every which way direction. So they could be moving east-west, north-south, and in and out, okay? On the average, the temperature measures how much agitation is, if you wish, in this gas or in this system in general. So from this point on, you probably will hear me use the word gas more often because it's easier to study than solids, but we will get into all of them. Okay. So temperature is a measure of how fast these things are moving. I cannot really relate to the speed, to the velocity by itself, because if I average the velocity in here, I will get zero. Because on average, if half of them are moving this way, the other half are moving the other way. So on average, this amount is zero as far as the velocity. This must be the velocity squared. The velocity square will make more sense then, because this average will, whether you're going this way or the other way. So when you square the quantity, or when you take the speed per se, it's going to not be zero. And that is how temperature is related to that. So it could be, for example, speed to the power 4. It could be speed to the power 6. For all we know, it's proportional to the speed itself, the magnitude of the velocity. Okay. Chapter 18 will clarify that, and actually will have an understanding that the temperature is really the measure of half the mass times the average of the velocity squared, which is the kinetic energy per particle. Okay. So at this point, it's too early to really make that point, but in chapter 18, we're going to explore this idea, and it's due to Mr. Boltzmann, who introduced it and basically explained what temperature is. Heat, on the other hand, is not. Okay? Heat, first of all, people were confused about it. They didn't know what it was. Because if I take a cup that is hot, and on a cold day, for example, I see stuff coming out of it. I see gas coming out of it. I see the evaporation basically of that hot cup, okay? And vice versa. If I have, for example, a system that is cold, they can see the condensation towards it, material going in it. So people associated, they thought it's some sort of a fluid, okay? And they actually gave it the word calorific fluid, or the fluid of heat, if you want to call it that way, okay? So calorific fluid was an idea to explain what heat is. And we defined at that time heat, or at least 1 calorie of heat, to measure its unit, really. So 1 calorie of heat, we are still don't know at that point what heat was, okay? So 1 calorie of heat is the amount of heat needed to raise the temperature. So we don't know what temperature is, so let's leave it for a second, okay? The temperature of water from 14.5 degrees Celsius to 15.5 degrees Celsius. How much water is it? of 1 gram of water. Because it matters. If you bring more water, 1 gram of water. If you bring more water, you need more heat to raise that temperature, okay? So if you bring 1 gram of water and basically measure its temperature and know its temperature is 14.5 degrees Celsius, then wait until the temperature, you see the thermometer rose from 14.5 to 15.5. Then you say, I have added 1 calorie of heat, okay? So the amount of matter matters, really. The amount of water in this case matters. So if instead I did not really bring 1 calorie per se, but I mean 1 gram per se, but I brought 1 kilogram, then I'm going to just redefine my units. That's all. So if instead I have 1 kilogram, then I'm going to call by definition 1 calorie. I want to bring your attention to the way C is spelled in here. In this case, it's lowercase. In this case, it's uppercase. That's all. So this is uppercase C, and this is lowercase c. Okay, that's the difference between the two. Again, 1 calorie of heat. So I'm going to just put in here is the amount of heat needed to raise the temperature of water from 14 degrees Celsius, 14.5 degrees Celsius to, again, to 15.5 degrees Celsius of 1 kilogram now of water, okay? So everything matches the same, except now we're talking, instead of 1 gram, we want to talk about 1 kilogram, because how are you going to work with 1 gram? So that's why we define the calorie. Clearly, from this conversion between a kilogram and a gram, it's 1,000 grams. So in this case, it's clear that 1 calorie, by definition, from these two definitions, is equal to 1,000 calories. So the spelling of this calorie matters a lot on how you write it, okay? Again, we still don't know what calorie is. We don't know what heat was. Until Mr. Joule did an experiment, and in his experiment, he basically proved without the shadow of the doubt that heat is actually energy. So what he did was he had this container of water, okay, where he ran an axle in here that is connected to flaps in here. That can spin. So he ran a string in here around it, and then he conducted this around the pulley, and then he put a mass in here. Obviously, it has weight, mg, okay? And he dropped it from a certain height. He can calculate the energy in this case. The energy is simply mgh. This is the energy, gravitational energy. He has a thermometer also attached to this device, okay? And the thermometer was measuring the temperature. So if this temperature was 14.5 when he started, and the amount of fluid, for example, did we miss a lot? Because we were disrupted, and I see that Zoom was frozen. I'm sorry, okay. So did we get to this point in here of the argument that Mr. Joule basically was making? So basically he took 1 kilogram of water and sitting, for example, at 14.5. I really don't have the exact data of what he did, but we can have basically a summary of his work. And if you note that the temperature rose from 14.5 to 15.5, you say in this case, you know it's 1 kilogram, so you know it's 1 big calorie. But he can measure also this energy from this side, and he found that 1 big calorie, basically is equal to 4,190 joules. Okay, joules at that time was not named joules. It was named afterwards after him, okay? Anyway, so this is from this point on, we know that heat is actually an energy, and it's not just any energy. It's an energy of transfer, in this case, between 2 points. So it's just like work, because this is actually the work that the gravity does in moving the object from this height to this one. So energy, the heat now from this point on, we know it's energy. It's measured actually in the same units of energy. Heat is energy, okay? Is a form of energy, because energy is so many forms, okay? Okay, hopefully this point went through. And so the idea still is, what is temperature? And for that, we needed something else, okay? So what is temperature? Obviously, temperature is what we feel. You and I, for example, today is a cold day, we can feel it. We have an intuitive notion of what temperature is. We have a feeling of what temperature look like. And that feeling needed to be translated to a number, because I can't really compare things if I don't have numbers, if I don't have stuff to measure with them. So what we did in this case is, what we noted actually is objects tend to, when they reach something we're going to call thermal equilibrium, because, and again, we really don't know what those things are yet, but we're going to define them as follows. Take a system. Again, I'm going to take the analogy with the hot cup, okay? Coffee, for example. Put it outside in room temperature and wait. You note that that cup of coffee will ultimately reach a temperature that feels the same thing, like that of the surrounding. It's not going to feel any hot anymore after a while, okay? So what we say in this case is that it has reached thermal equilibrium with another one, with the air. So I must have two objects to do thermal equilibrium. I must have a system A, like coffee, for example, and I must have a system B, like the air, for example, in the room. And I must do something between them. I have to establish thermal contact between them. If I isolate one or the other, then I notice that this thing is not going to happen. Thermal equilibrium is not going to happen, okay? So the idea in here is that if I establish thermal contact and wait long enough, these two systems will reach thermal equilibrium, okay? So if we wait long enough, the two systems, this is system B, by the way, the two systems will reach thermal, or will be in thermal equilibrium, in which case I say, equilibrium, that they have the same temperature. They have, meaning they have the same temperature, because I actually can feel that too. Since we're going by the feeling now, leave your cup of coffee for a few minutes, if it's not long enough, for a few hours, if it's not long enough, for a few days, and ultimately, when you feel it, it's going to feel exactly like what room temperature does. So in this case, you say, oh, the two have reached thermal equilibrium, okay? So this is going to be a means for me to invent a thermometer. So let's do that, okay? Here is the Zeroth Law of Thermodynamics. This is the discussion that we're going to have today, okay, for the Zeroth Law of Thermodynamics. So this is going to be a way for me to measure temperature. Let's state the law first, and this is going to be the discussion item today. We have system A. We have system B. And we have system C. let's assume that system A and system B were in contact and have reached thermal equilibrium. So they are in thermal equilibrium. Let's also assume that system B and system C have been in contact, in thermal contact, and too, they have reached their thermal equilibrium. So do you understand the assumption here? This is a condition. This is another condition. Those are two different conditions. In other words, I bring system B and make it in thermal contact with both system A, and then make it in thermal contact with system C. And if they reach the thermal equilibrium, then I say in this case, the Zeroth law basically states that both system A and system C are also in thermal equilibrium. That sounds intuitive enough. Then, so this is the conclusion that system A and B are also in thermal equilibrium. So I drew it in here in diagram, hoping that you guys can put it in your own words. Basically, the Zeroth law said the following: bring a system B, compare it to a system A, and then if they reach thermal equilibrium, you can take system B now and compare it to another system C and watch. Do they reach thermal equilibrium? If they do, then in this case, the conclusion is that system A and system C were actually in thermal equilibrium, or they are in thermal equilibrium. So let's take system B as my thermometer now. So that is basically the whole point of it. So system B could be my thermometer and system A could be water. So this is the idea. I'm going to take water, for example, and I know how to add its, change its temperature. I know, for example, that water freezes at some point. If I add to it a certain amount or extract from it a certain amount of heat, and it boils at a certain point, okay? Now bring a thermometer made out of doesn't matter what, made out of, for example, an alcohol or something like that. And, oh man, this is terrible pictures, okay? Let me get straight lines in here, that's probably better. Can I do a straight line? Okay. Still bad. Sorry. Let's delete that. Bring this one in here. So this is my thermometer, okay? So the way thermometer in this case, this is system B, by the way. So this is my system B, and this is the water that I know how it works, system A, okay? So where the temperature is sitting at 0 degree, I'm going to, where it's boil, where it freezes, I'm gonna call it 0 degree in this case, okay? Somebody else called it actually 32 degrees. So it's your scale, really, how you're going to do it. That's all, okay? So where the water freezes is going to be your point in this case. Then, where water boils, for example, I'm going to call it 100 degrees. So this is 100 degrees now. I'm going to call this 1 degree centigrade, and I'm going to call this 1 degree centigrade, whereas this guy called it 212 degree Fahrenheit. The reason why it's centigrade or Celsius is because it's the 100 divided into 100 pieces. So the distance from here to here, it's basically spaced to be 100. So I can take that distance and divide it into 100 pieces and call this one, the next degree is 1, and so on and so forth, all the way to 99 degrees and 100. As a matter of fact, I can go above that, 101, and so on and so forth, 102, and so on and so forth. Same thing in here. It doesn't stop at 212, so you can go any higher in here you wish. As a matter of fact, we can go below that too. Okay, if you keep on extracting more and more heat, ultimately the temperature will go below 0 or go below 32 degrees Fahrenheit. Okay, so this is basically one way of measuring. Now, this is system A and B. Now we really have another system, C, something else, okay? So we take our thermometer now, properly scaled. So this is the scale on it. How we're going to define the scale, it's really a matter of convention at this point. Then bring another system in here, system C, that is sitting at some temperature, okay? and make it in thermal contact with my thermometer. Let's say, for example, the temperature is reading 72 degrees Fahrenheit, okay? Or if you wish some degree in here, I don't know. Let's say, for example, 29 degrees Celsius. I don't know. I don't think it's correct, okay? It's probably 24, okay? 24 degrees Celsius, okay? We're going to do the conversion very shortly. Anyway, the point being in here is that this thermometer or the other one are just telling me how system C really would compare if I add or subtract a certain amount of heat from some water and bring it to that level of temperature. So that is basically what the thermometer is. So it's really comparing, in this case, water to an object. And it's really the middleman. It's system B that I can take and carry with me now. Since I probably already scaled it, it's already probably, it's not probably, it's already correctly scaled, correctly gauged, correctly everything. So I know what, based on an object that I know, like water, for example, then I can use that to study the temperature of everything else. So from this point on, we have a measure for temperature. So this is what the zeroth law allows me to do, and that is to measure temperature. Okay, it allows for the invention or the justification for a thermometer, basically. Okay, obviously, where to choose the zero is really a matter of convention. Anybody can have his or her own system, but most of the people in the world, they use the degree Celsius, and that's probably what we're going to be using at this point. The advantage of the degree Celsius, it's really nicely scaled in this case. It goes from 0 to 100 in the divisions of 100, whereas this one is kind of from 32 to 100, 212, that is 180 divisions. So this one is finer. So in other words, the distance between a degree Celsius and let's say, for example, 0 degrees Celsius and 1 degree Fahrenheit, 1 degree Celsius, I'm sorry, is and the 0 degrees Fahrenheit and the 1 degree Fahrenheit, obviously they don't correspond to one another, actually 32 degree Fahrenheit. The next degree, 33 Fahrenheit, doesn't sit in here. So this is finer distance between the scales. So if somebody is picky and trying to keep up with the slightest variations in temperature, you're better off using the Fahrenheit. If you don't care about that finer distance, but you really care about the overall to be in a more uniform way to converting, then in this case you use degrees Celsius. So it's really a matter of convention which one you like to use. Okay, so that is really the difference between the two. As a matter of fact, there is a conversion between one to the other, and you will need these formulas basically for some of the homework problems. So the derivation for it is not hard, by the way. All you have to do is just find you assume that there is a linear, and it is linear because they're both comparing with the water in this case, of how temperature in Fahrenheit depends on the temperature in scale, the temperature in Celsius. So what you say in this case, I have the points. So you're going to draw, for example, the function t as a function, tf as a function of tc. So it's going to be a line of some sort, okay? And this line, in this case, you know 2 points on it. You know already the point that is 0 degrees Celsius, okay, correspond to the point 32 Fahrenheit. This is the y-intercept, actually. So this is the point 032. And there is another point in here. So this is 0 in here, actually. And there is another point in here, 100 degrees Celsius, will correspond to another point, which is 212. Okay, so this is 100, 212, and then it's a matter of just finding the slope, which is just 212 minus 32 divided by 100 minus 0. So the slope is going to be 180 divided by 100, which is 9/5 really, times TC plus the y-intercept, which is 32 in this case. Okay. So it's easy to derive, actually, and use this expression to find Tc as a function of Tf. So if you're given the temperature in Fahrenheit, you're going to take Tc, in this case, is going to be 5/9, move the 32 to the other side and subtract it from T in Fahrenheit. Again, the answer is going to be in Celsius in this case. So There is it's not hard to convert from one to the other, but that's the point in here. The point in here is that the scaling in TF is a lot finer, and that's why you're going to shrink it a little, okay, to make it. Did I say it? Yeah. Okay. So this is basically the point that that has to do with the conversions. Here is where people were. I mean, this whole chapter is really kind of fun a little bit, okay, because it doesn't have a lot of integrations and stuff like that for you guys to worry about. Here is something that we have to, since we're talking about scales and temperatures, people were dealing with this kind of gases. They wanted to really understand the relationship between temperature and pressure, for example, okay, or volume and temperature, or pressure and volume. So what they do in this case is they fix the pressure, they fix the temperature. When the temperature is constant, they take a gas and they started working with specific kind of gases. Those are the so-called ideal gases. Those are gases with low density enough in them so that they can do these studies. Otherwise, these studies a little bit are not correct. So we're going to be not correct. I mean, they're hard to do. So we're going to be dealing with ideal gases basically, and later on we will see what these ideal gases look like. So for an ideal gas, when temperature is fixed, the ratio of the pressure in one section, I mean at a certain temperature, and the pressure at another, basically, I'm sorry, the volumes, at different volumes, the ratio of the pressures is inversely proportional. In other words, P2 V2 is equal to P1 V1, okay? Then when we experimented again with the fixed volume, in this case, we noticed that the pressure and the temperature are proportional to one another. And when we fix the pressure, the volume and the pressure seem to be consistent with one another. So basically, this ideal gases has this law for them, PV equal to some constant. That number N has to do with the number of moles, how many moles you have, and R is a constant. R is equal to 8.314. But this temperature in here seemed to be shifted. So we really need to fix, either we were using, actually people were using the centigrade at that time. So this is basically what they have observed for a gas. So if I take, for example, the temperature, this is where my 0 degrees Celsius is, and this is, for example, the pressure of that gas, okay? If I study that for gas 1, for example, the pressure and the temperature, they go like this. They didn't have a lot of means basically trying to, so that they can lower the temperature below a lot of degrees, below degrees Celsius, because at that time the technology was not well advanced enough. But the next gas will behave like this, the third gas will behave like that. If you take these points and extrapolate them, so by extrapolation, all of these points, they seem to, regardless of what type of gas, they all seem to meet at negative 273.15 degrees Celsius. It seems that at that point, the pressure drops to 0. Obviously, at that time, we didn't have good enough technology to reach that temperature, but that's basically by extrapolation. So they extrapolated the data, the observations. Now, today, we cannot reach that temperature either. Nothing can reach that temperature. We know that this is actually a theoretical limit. You cannot reach it. Even the universe outside. I mean, you know, inside a star, it's super hot. But if you move away from the star, it gets colder and colder. So assume you're in interstellar space and there is nothing in there, complete emptiness. It's still, the temperature is not 0. It cannot be 0 Kelvin. It has to be, it's actually 2.3 Kelvin. That's the lowest that it exists today in the universe. So temperature 0 Kelvin is really an ideal situation, which brings me to the scale Kelvin, where everybody shifted, in this case, the scale from 0 degrees Celsius by this amount. And now we're going to be using the temperature T in Kelvin. So T is actually in Kelvin, and if you're curious what is T in Kelvin, so this is actually how we measure temperature, is T in Celsius, okay? Added to it, 273.15. So that's going to be your T in Kelvin. So for temperature, for example, in here is 0 degrees Celsius, it's, as a matter of fact, 273 Kelvin, okay? So with that correction, this law now looks better. So this law now, PV equal to nRT, this T is not in degrees Celsius, not in degree Fahrenheit, not in Rankine, which is another unit, but rather it's in Kelvin, must be in Kelvin. So whenever you're doing your calculations for the homework or the exams or questions or something like that, don't think T, if they give you T in Fahrenheit or degrees Celsius, that's the value you're going to be plugging in. You're going to plug in the value shifted by this amount, 273.15 to be more precise. Most of the time you will see me using 273, okay? So this is the temperature in Kelvin and not in any other unit. R now has a number. R is a constant. R is actually equal to 8.314. The unit for PV is actually joules. N is just the number of moles. So we're going to plug it in here. Okay, how many moles you're talking about? So it's per mole. And then T is actually in Kelvin. Okay, note another thing also. We don't say degree Kelvin. We say degree Celsius because that's how we define the scales in here. Degree Celsius, degree Fahrenheit. But we don't say that for Kelvin, because now it's really defined properly so that it's like a unit right now. So it's where the temperature basically or all the pressure of all of the ideal gases drop to zero, which is theoretical limit, because what does it mean to have zero pressure? It doesn't mean anything. So in this case, it doesn't exist, not just because of that, it doesn't exist because of also there is another physics that is lurking out there at those temperatures, and that is quantum mechanics that prevents you from reaching that point where where everything freezes from moving, because at that time, because that's basically what that temperature is. Remember my definition earlier, or at least my remark concerning temperature to begin with, that temperature has to do with the agitation of the molecules. So if the temperature really drops to zero, that means the molecules or whatever makes that object stops completely at its tracks. And there is no such a thing. At that point, when you reach that level of temperature, there is still quantum fluctuations that will prevent you from reaching this temperature. So that's why this is a theoretical limit. You cannot really have an object that reaches that 0 Kelvin, because that is basically what the point in here. 0 Kelvin will correspond to Tc equal to negative 273.15. In the lab, we arrive very, very close from that, but we will never be able to reach it because you can't. It's not because you don't have enough technology, because it's a limit that cannot be reached. Okay, so zero absolute zero is unreachable. Zero Kelvin is unreachable. Unreachable again. How should I say? Is impossible actually. Possible to exist. Okay, period, end of story. So that is the lowest. I mean, higher temperatures, you can have trillions of degrees if you want to. I mean, the known stars, for example, some of the stars, they can have 212, 220, 250 billion degrees of temperature. In that case, it doesn't matter which unit you're using, degrees Celsius or Kelvin, but they could be tremendously hot. But that is basically, so the upper limit is there is no limit to it, but the lower limit for temperature, there is one, and that is this one, okay? So from this point on, basically this law that we're going to be using in here, PV equal to nRT extensively in this part of the class, basically, are you guys familiar with this law? Did you guys have it before in chemistry or something else? Maybe? Did any one of you have chemistry already? Okay, thank you, Daniel. Okay, the idea in here is that it's going to be used in a little bit different context, and we're going to have a justification for it in chapter 18, okay? So we're going to come up with some sort of why this is true, okay? So again, PV is in joules. Okay, some of you probably had it in chemistry and they use this different system in there. There's the different units. Please disregard that one. I know probably will some use at some point, for example, for pressure, it's used in atmospheric pressure and the volume is in liters. So in this case, this energy is going to be in ATM liters, in which case R will have a different number. But if you remember this number in SI, then in this case you can convert the atmospheric pressure to normal pascals. So basically 1 ATM, 1 atmospheric pressure is equal to 101,300 pascals. And then also the 1 liter, which is also used in that case, is going to be equal to 1,000 cubic centimeters, or cubic centimeters, or equal to 1/1000 cubic meters. Okay, so if you remember these conversions, you're going to be fine in terms of this. You go back to joules, and the number is 8.314. That is what my worry about this number R in here for the constant. Okay, so this is basically where we were at that point in here in terms of thermometer. The zeroth law allows it to do that. Please put the zeroth law. So this is as an item of discussion in your own words, so that basically you are familiar with it, and it's the one that allows us to invent the thermometer, so everything was good. So let's go back to that idea of heat, because we said for water, Q, it's still, this is heat, by the way, this is the symbol for heat. Q is in calories at this point, okay, is equal to M times C. C in this case is 1 because all we did was say, okay, it's the amount of heat in calories per 1 gram for the temperature to go by 1 degree Celsius. By the way, 1 degree Celsius, so if I'm measuring the difference in temperature in this case, whether I use TC plus 273, subtract from it, so this is 1, minus the second temperature, TC plus 273, times 2, the second temperature, is going to be basically, regardless of how I'm going to write it, temperature in degrees Celsius, this is the temperature in Kelvin 1, and this is the temperature in Kelvin 2. So whether I write it in degrees Celsius or I write it in degree, or I write it in Kelvin, it doesn't matter. So delta T is an exception to the conversion in there. You don't need to convert if all you care about is just the difference between temperatures. Because if you add 273 to one and you add 273 to the other and take the difference, the 273 will cancel. Okay, so for the difference in temperature, like we defined, for example, the specific heat, we defined the heat earlier in here, because we said it's 1 calorie of heat, amount of heat needed to raise the temperature of water from 14.5 to 15.5 of 1 gram of water. So in this case, we're just talking about the difference between 15.5 and 14.5. So in that case, it doesn't matter if I add 273 to this one and 273 to that one, the difference is going to be 1. So in other words, the difference 1 degree Kelvin, on the scale of Kelvin, so you're going to go for the difference in temperature between the two adjacent temperatures is going to be 1 Kelvin, which is exactly equal to 1 degree Celsius. And like what we said earlier about the Fahrenheit, which has that 5/9 ratio or 9/5 ratio. Okay, the scales are different for that case. Okay, they are finer in the case of the Fahrenheit, but they are the same when it comes to Kelvin and degree Celsius. That's why when we're doing this expression here for specific heat, it doesn't matter. You don't need to convert, in other words. Just leave it the way it is if you like to keep it the way it is. If you want to be safe, then sorry, go ahead, convert, but the difference is going to be the same thing. Okay, is this point clear about this delta T business? Come on, guys. I know it's too early with the time change, but is this point clear that you don't need to convert when it comes to delta T? But when it comes to PV equal to nRT, it's a must. You don't have a choice. Yes? Okay, very good. Thank you. because it's a difference in this case, so you don't need to convert because the scale is this, I mean, it's the difference between the two temperatures. So this basically defined for me the calorie. So what I say in this case is this is in little calorie, this is in grams, and this is in degrees Celsius, if you wish. It doesn't matter. In Kelvin, it's the same thing. So this quantity, I'm going to say 1, because if I take the same amount of heat and try it, for example, on a different substance, for example, iron, I see the temperature rise super high for the same amount of heat. So if I bring 1 calorie, for example, and I notice that the water temperature rises from 14.5 to 15.5, so I know exactly that this is exactly 1 calorie. But if I take the same amount of heat, that 1 calorie, and apply it to the same amount of matter, of iron, in this case 1 gram, I notice that the thermometer reading will skyrocket, will give me a very high temperature. So in this case, it seems like, I'm sorry, yeah, it seems like there is a quantity in here that is specific for every single element, and that is why we have the specific heat in here. So this is what distinguishes water from iron, specific heat. Okay, what distinguishes different materials altogether. So the heat in general, then the formula for the heat is going to be the amount of heat needed is going to be m, the amount of mass, because if you have more mass, you're going to need more heat to raise its temperature, times c, in this case, the specific heat of the element, times delta T. Water happened to have 1, the specific of heat of water, C of water, happened to be just 1 calorie per gram per degree Celsius, or 1 capital C calorie per kilogram per degree Celsius. It's the same thing, right? Lowercase c, capital C, lowercase g, I mean gram and kilogram in there. So this is the specific heat of water. The specific heat of iron must be a lot less than that of water, because you don't need that much heat to raise its temperature by 1 degree. So it really takes heat easily, more easily than water. So water has an unusual high specific heat. Okay, so that's basically the conclusion of this part in here. So if I take water again and mix it with, for example, let's say, for example, I have water sitting, for example, at 20 degrees Celsius. And let's say, for the sake of argument, I have, for example, a liter of water, which is 1 kilogram, okay, of water. So this is the mass, okay? Because I know that the density for water is 1 kilogram per liter. So if I bring a liter, I brought 1 kilogram. And let's say, for example, I bring, for example, for the case of argument, and for the sake of argument in this case, the iron, and I bring iron in this case. What's the specific heat of iron? Okay, get this out of the way. This is part of your experiment, by the way, part of the lab today. We're meeting today for a lab, okay? So the specific heat of iron is going to be 0.44 joules per gram per degree Celsius. So if you want to find it in kilogram per degree Celsius, all you have to do is multiply this one by 1,000, and it's going to be 444 joules per kilogram per degree Celsius. However, the specific heat for water, let's say, for example, this is sitting at 140 degrees Celsius, okay? And we brought how much? Let's say, for example, we brought 50 grams, okay, or 100 grams, okay? Or 0.1 kilogram, 100 grams, and put it inside, okay? It's more than boiling. It's 140 degrees. It's hot, okay? And you put it inside. and you would want to see where the temperature is, you will see that the temperature doesn't move much from 20 degrees Celsius. In other words, this one will come down drastically from 140 degrees Celsius to closer to where the 22 degrees Celsius, because the specific heat for this one is 1 big calorie per kilogram per degree Celsius. Or remember, the conversion is 4,190 joules per kilogram per degree Celsius. Okay, so I want to know what's the equilibrium temperature in here. Let's say, for example, I lost this much heat in here to bring this temperature from 140 degrees down to the temperature of equilibrium. So once I reach that point, the amount of heat lost to cool it down from 140 degrees down to the new temperature is going to be the amount of iron, which is 0.1 kilogram, that's the mass, times the specific heat, which is 444 joules per kilogram per degree Celsius, times the difference in temperature. We were at 140, now we are at a new temperature to equilibrium. This heat must be equal to the heat that was gained by the water, because if I put it inside, and let's say, for example, this material is negligible specific, I mean, it doesn't enter into the problem, we're going to neglect the effects of the container. So we're going to say, for example, that the Q now that was gained by water. Okay, so the water's temperature now is going to increase accordingly. So it's going to go 1 kilogram, 1,000 grams, and I need 4,190 degrees, 90 joules per Kelvin, per kilogram per degree Celsius, times the water temperature rose from whatever it was, 20 degrees now, up to T equilibrium. I have an equation now to solve for this temperature. So if I equate the two quantities, first of all, the kilogram cancels the kilogram, the degree Celsius will cancel degree Celsius. So at the end, basically, the joule will cancel the joule. So everything will be the same thing at the end. Yeah, so if I equate these two quantities, so I say 0.1 times 444, which is 44.4 joules per, the kilogram is canceled already, kg canceled kg, so per degree Celsius, times the, what is it, 140 minus T equilibrium is equal to 4,190 joules per degree Celsius times T equilibrium minus 20 degrees Celsius, okay? So if I solve this equation in here, I will end up with basically an equation for T equilibrium, and T equilibrium is going to be 4,190 minus, if I take minus to the other side, it's going to be plus 44.4, okay? This is T equilibrium. I took this side to the other one, so it became a plus. Now, if I bring this side to the other one, it's going to be a minus, is going to be a plus. So it's going to be 44.4 times 140 plus, again, 4,190 times 20. And from here, I'm going to divide the two. So I'm doing this quick in here, hopefully, for you guys to see how to do calorimetry, because you will need this one for your, let me move the, I know you want to see probably the calculation. Hopefully you guys have access to a calculator quickly to find the temperature. So it's going to be open parentheses, 44.4 times 140 plus 4,190 plus, times 20 divided by, open parentheses, again, 4,190 plus 44.4. And that should give me 21.2 degrees, okay? 21.2 degrees. So the equilibrium in this case is 21.3, okay, if you want to round it, okay, degrees Celsius. So you know that the water's temperature went from 20 degrees up to 21.2 degrees or to 21.3 degrees. It took all of that heat and it raised its temperature barely above 1 degree Celsius. Whereas it dropped this temperature from 140 degrees down to 21.3 degrees. So he dropped it by 119 degrees because the specific heat for iron is a lot less than that of water. So again, I hope that you guys see through this example on how to do your calculations and stuff like that from here. Okay, we still have a few minutes. I know that probably you did this example in chemistry, and this is a calorimetry example, and that is going to be part of the lab this afternoon, so that we can go through this how to do this experiments. You take different samples of different materials. You're going to put them in different water at different temperatures, and you're going to find the specific heat and do these calculations. Now, if you don't have things in Joule, you have to convert them in Joule. And the specific heat for water is 4,190 joules, basically, per kilogram per degree Celsius. If you wish, it's 1 big calorie. If you want to use the calorie as a unit, 1 big C, 1 calorie per kilogram per degree Celsius. And calorie in this case is 4,190 joules. So that is basically the stuff that is related to the calorimetry, which is, again, there is another time in here where the change in temperature will be so drastic. This is assuming the specific heat doesn't change with temperature. The specific heat sometimes changes with temperature. So this expression assumes that specific heat is constant. At some point, for example, about 100 degrees Celsius, the water, for example, becomes vapor. So you're going through a phase transformation in this case, okay? So you're going from one phase, which is liquid, to another phase, which is solid. So how much heat will you need? It's going to depend on, first of all, the material and the amount of it, okay? Where L in this case is going to be the energy needed per unit mass. So it's going to be, again, the units for L, and they're going to be specific for it. For this one, it's going to be joule per kilogram. So if you're going to go from gas to liquid, from liquid to gas, you're going to add heat. If you're going to go in the opposite direction, you subtract heat. That's why you see this expression most of the time has the plus or minus in it, because depending on which direction. Are you through condensation? Or you evaporation? If you're evaporation, the quantity Q is going to be positive, and if you're going through the condensation, is going to be negative. This expression also is true in the case of freezing and melting. But the values in there are different again, okay? So you're going from one phase to the other, and the L in this case will depend on the material. And this is the condensation, and this is the evaporation. Again, when you have a substance, let's say, for example, you have water solid sitting at -10 degrees Celsius, and you want to bring it to 10 degrees Celsius. So calorimetry in this case would be very, very hard problem to, not very hard, very methodic problem to follow. For example, if I take ice sitting at -10 degrees Celsius, and I add to it that same quantity of iron and see which temperature is going to reach, it's not going to reach what you might think. First of all, it's going to raise the temperature from -10 to 0. And at that point, you need heat to convert all of the water, all of the ice that was at 0 degrees Celsius, to water at 0 degrees Celsius. Okay? So you need to have this equation in between to go through the phase transformation, and then add more heat if there is enough to raise its temperature from 0 degrees Celsius. So the situation might end up with the temperature below 0 degrees Celsius, temperature at 0 degrees Celsius, or temperature above 0 degrees Celsius, and you have to take this equation into account, not just the first one, okay? So when you're doing calorimetry, you have to be very careful with, especially if you're going to go from one phase to the other. Had we have brought a lot of iron, for example, in this first example, and the temperature of the water still was 20 degrees Celsius, and we calculated, for example, using just calorimetry, and we found the temperature to be 110 degrees, we brought a lot of iron, basically, and made the water so hot that its temperature now is higher than its boiling temperature, then in this case, the calculation is wrong, because we didn't take into account this temperature. We didn't take into account the evaporation. So in this case, we will do another calculation, see how much heat is needed first to bring the temperature from 20 degrees Celsius to 100 degrees Celsius to the boiling temperature, and then how much heat is actually went to converting that amount of mass of water into evaporation, and then if there is left heat in it, if there is enough heat left, then see if it raises its temperature. Most likely the temperature is not going to be 110, but rather probably it's 102 or 103, because you needed some heat first to go through a phase transformation. Okay, so that's basically the point of this discussion in here, which brings me to the last 2 points of this chapter, and that is how heat is transferred. Okay. Okay. There are 3 ways for heat to go through from one system to the other. First of all, convection. Convection is a little bit hard to put it in math at this point, because it involves the circulation of the air masses. It involves the circulation of fluids. It involves the circulation of even solids. In the case of the Earth, for example, under its mantle, where the different parts of it are moving. So it's matter carrying heat with it. Okay, while it's motion. In the case of the air, it's the air masses, again, moving from a hot region to a cold region and carrying with them heat. In the case of boiling water, for example, that's the same mechanism where heat is transferred by the motion of the fluids. Same thing is actually happening in the sun. In the core of the sun, there are nuclear reactions where the temperature is 20 to 100 million degrees, I'm sorry. And at that point, it's super hot. But the surface of the temperature is only sitting up around 5,500 Kelvin. So what's going on in this case, there is a transition between the two where actually heat is transferred from the core of the sun and releasing basically all of that heat. Otherwise, the sun will be increasing its temperature indefinitely and basically getting rid of that heat on the surface and falling down and so on and so forth. So again, it's a circular motion. So this is cold region, cold air. This is hot source. And the air in here has a higher density. The air in here has a lower density. So the higher density will fall and the other one will rise just by buoyancy, basically. Okay. So now it cools down. As it cools down, it's going to fall down and so on and so forth. And that's exactly the bubbles you see during when you're cooking soup, for example, okay? Because you are immediately in the bottom of the soup, you are in contact with the thermal source, which is in this case a furnace, and then in the top, which is in contact with the air. So in the contact with the air is a lot cooler than in the one of the furnace, so the water will circulate in this circular fashion, it rises, lowers its temperature, becomes denser, falls, because dense will fall, and then the bottom now gets heat, increases its density, and then it rises and so on and so forth. This is the circulation of air masses. This phenomenon is associated with the weather. Basically, it explains perfectly the weather and what's going on with it, especially if you combine it with a specific heat for water, and why water is really the main mechanism and why the oceans really play a major role in terms of the weather and planet is because of this mechanism on how the heat is transferred from a region of the planet to the other, and that is convection. Okay. Another way of doing it is through conduction. The rate at which heat is transferred, namely power, dq over dt, sometimes it's called the current, okay? This is what you feel as breeze, current of heat, okay? So this is a power. This is the rate at which heat is transferred. It's proportional to the area, first of all. If you have a bigger area, you have more heat going. If you have a smaller area, you have less heat, okay, leaving that area. It's proportional to the area. It's proportional, of course, to the gradient in temperature, how big the temperature is. Again, this is experimental results, okay? So if there is a big difference in temperature, then there is more heat transfer. If the two sides are sitting close from one another, there is less heat flow between one region and the other. So this is the gradient in temperature, or difference in temperature, divided by the length which the heat is going to transfer. If the length is very long, then the rate is very slow. But if you have thin walls, then in this case, the heat escapes at a higher rate. So again, the length in here, or the depth through which the heat is to flow. Now again, depends on the material. Each material has its own conductivity. So this is the conductivity of the material. conductivity. It has to be stated that this is thermal conductivity. Okay, it's a fact that a good heat conductor is also a good electrical conductor. So that is something that has to do probably with the motion of the electrons inside the material. So again, this is in joules per second, the unit for it, or watts, which is the same thing. Okay, so this is the amount of heat that is transferred per unit time, the rate at which the heat is being basically leaking from one region to the other. So again, it presents a problem. If you want to have insulation, what kind of material you need there? What kind of K you need there? What kind of area you need there? What kind of depth you need there? So, and that is basically your problem in this case to save. If you want to really get rid of heat, if you want to dissipate heat, then in this case, the problem becomes a reverse. So you need a good conductor, not a good insulator. So again, this problem has to do with the transfer of heat. Another also way for heat to transfer, so this is by conduction. The third way for heat to transfer is by radiation. The first two requires media. This one and that one requires actually a medium. So again, this is item 2 of the discussion. Please list ways for heat to transfer. List ways for heat to transfer and give some examples, okay? In other words, show understanding. The third way for heat to transfer is by radiation, okay? Heat will transfer in the same thing at the rate of dq by dt. This is again per unit. Sometimes we use a symbol H for this quantity, okay? For H for heat in this case, okay? So this is again, H in this case has a unit of power in this case, okay? So again, it's going to be proportional to the area, okay? And it's proportional to something called the emissivity of the material, or coefficient of emission. Two S's. Is this two M's? Coefficient d'émission. No, I think that's only one M. I'm not sure. I need to fix my stuff in here. Okay, so this is the dependent, not plus another coefficient in here. I'm going to call sigma. Okay, this is constant. This is 5.67 times 10 to the negative 8 always. Okay, 10 of course times the temperature. And here I'm going to fix the temperature quickly, and we'll talk about why that thing is in there. T to the power 4. Okay. It's not a delta T, but T itself, okay? The units are going to be in watts. This coefficient has no units, just a number between 0 and 1, which is 100% is 100% emissive, and 0 is completely absorbent, okay? So that's basically what, that's why sometimes it's called the coefficient of absorption, okay? Watts per meter squared, that's the area, per Kelvin to the power 4, okay? So this is the units for this number. Sigma is a constant. Sigma, it's the Boltzmann Stefan constant. And this is actually called the Boltzmann Stefan law. Okay. Down the road, when we study the black body radiation and we explore, it's not going to be probably in this class, maybe in physics 4C, and we explore other ideas basically related to this radiation. Basically, it has to do with the electromagnetic waves. It has to do with the light, because the sun, we can see it because the electromagnetic light travel through vacuum. And this does not require medium, by the way. No medium required. Because it can travel through empty space, okay? So the mechanism through this one is actually through the electric field and the magnetic field traveling through empty space. And that is basically what we're looking at. Because if this was not there, If radiation was not the phenomenon basically through which heat is transferred, we will never be able to see the stars. The stars, the only reason we see them because there is an empty space between us and them. A vacuum is through radiation, and that's basically how we can see this thing in here. Again, sigma is a constant, and it's 5.6710 to the -8. It's a tiny constant in this case, but T matters. T to the power 4 is a big deal in here. So this is not a difference in temperature. This is just basically a temperature, pure and simple, meaning that if I have an object sitting at a temperature T, so this is an object, okay? And the surrounding is sitting at temperature C is surrounding, okay? Then depending on the difference, if the object is hotter than the environment, then in this case, the object will emit radiation, okay? So in this case, it's a net emitter of radiation, okay? And it's going to feel, in this case, cool because the environment is cooler than than that object because it's losing heat, okay? So it's getting colder and colder over time. If the opposite, if the object is cooler than its surrounding, in this case, the surrounding is actually transferring heat to it at this rate, okay, the difference between the two objects in this case. So it's going to be basically at this point, T to the power 4 and T to the power 4 times, again, the same coefficient sigma times A times E, and this is going to be H net, okay? The rate at which heat is transferring one way or the other, okay? So again, if the surrounding is warmer than the object, in this case, heat will be transferring back to the object, going in the opposite direction. And in this case, it's going to be absorbed by the system. Its temperature will start to rise, okay? I probably should have used the signs differently in order to get this net object in here. So I'm going to take it in absolute value in here, okay? And hopefully you guys understand the idea behind it, okay? The idea is that depending on which one is warmer, the temperature will transfer one way. If both of them are sitting at same temperature, in this case, there is no net transfer. In that case, we reach thermal equilibrium. Okay, in that case, we reached. This is the cause of why your cup of coffee is going colder over time. If you keep your cup of coffee outside, this is the culprit. This is the problem. Okay. If the surrounding is a lot hotter than your cup of ice, for example, this is the culprit also why your ice is melting, and the nice orange juice that you had sitting with ice cubes in it, now it's all of a sudden basically no good because it's warm, okay? So this is the problem for that too, okay? Okay, when we meet this afternoon, we have lab, first of all. Let me stop sharing the screen. And we have an important lab that you guys hopefully will join in. It's not hard to do, honestly, but it's a fun lab. So I want you guys to have at least a head start on it. And then when we meet on Wednesday, we're going to do problems. I think I already chosen 2 problems, maybe potentially 3. They're actually a little bit, this entire chapter should not be hard for you guys to do. The next chapter is going to involve the chapter on Kinetic Theory. Basically, this is due to Mr. Boltzmann himself. He wanted to explain what that ideal gas situation is, and he came up with an explanation for PV equal to nRT, actually. Instead of coming up with PV equal to nRT, he came up with PV that is proportional to the average of the speed square of the average of the basically kinetic energy of the molecules that make up the gas. Obviously, at that time, we had no idea that molecules even existed or atoms existed. So people made fun of him until he committed suicide. Some people basically blame the fact that people made fun of him for committing suicide, but they also say that probably has other issues. Anyway, the point is, this was really a foundation that led to a lot of discoveries. Among other things is explaining this phenomenon with radiation. It's a black body radiation because people tried to explain it. And really, when he tried to use the same ideas of Boltzmann, came up with some nonsense results, completely nonsense. It was actually Mr. Planck who came up with a better explanation, but his better explanation came up with at a cost that he himself did not believe existed. It means that the energy for the electromagnetic waves for some reason was not continuous, was quantized, obviously he went in life basically claiming that it was, people don't blame me, I just did a mathematical trick to solve a problem that Rayleigh could not have solved, nobody could have understood. And at the end, he won Nobel Prize for it because he discovered basically the onset of quantum mechanics. So even though he himself did not believe it, Planck himself did not believe it, he became basically a household name when it comes to stuff like that. There is a big institute, actually the biggest institute in Germany is named after him too now. Anyway, so I know we still have a few minutes. Do you guys have any questions for me? Don't forget we have class this afternoon, so at 2 o'clock, okay? So let me stop the recording then.